So to remind you about what we said last class, we basically discussed the mechanics of internal expanding rim for clutch and brakes. And we said that when we have an example here of a drum which happens to rotate along the clockwise direction, and we have the shoe over here. Maybe I should do it in blue. One shoe only. Most of the time we have two. Okay, and on the top of the shoe, from here all the way down there, we have the material, which is the frictional material. So just to tell you that the beginning of this is theta 1, the end of it is theta 2. These are two important parameters. The pin here is hinged, and we have two reactions, Ry and Rx. The force is been actuated by the F over there, and for force analysis, we split this force into two components, X and Y, and along an arbitrary line over here, we resolved the normal forces and the frictional forces, and basically these forces are going to generate moments, and this is why we got Mn standing for the moment resulting from normal forces, and Mf, which are the moment resulting from frictional forces. Before I go back to this equation and talk about energizing, self-energizing, and de-energizing, I should tell you that we have a few important parameters to worry about, which are the radius. The radius is there. This is the radius of the drum. So if the brake has a radius of a diameter of 500, then the radius is 250. And the C, which is the distance, be careful, from the pivot to the point of the actuating load. So it's the line which connect the pivot, which is there, to the actuated force. Now this is very important to understand. Why? Because the arrangement of the shoe could be different, right? Could be like this, could be on the side. So that distance might, in your head, may not be always inclined. It might be vertical, it might be horizontal. So be careful. The other thing is this A, the distance A is actually the distance from the pivot to the center of the drum. So again, that distance might change. Here, it is just a straight horizontal line. In some other problem, as we're going to see, it might incline. It will stay a straight line, by the way. Now, so these are very important parameters. Of course, just to let you know, that in this problem, we decided that the coordinate system start here as X and there as Y. Yeah? So, as we are going to see in the problem that we are going to solve today, you can make your life a little bit easier in terms of integration to avoid having to substitute theta 2 as an angle and theta 1 as another angle. You can just put theta 1 as 0. How? By shifting the coordinate system. So you can actually make the coordinate system here as X, and then perpendicular to it, you will have Y. And in that way, theta 1 will be 0, and theta 2 might be 90 or 30, 100, it doesn't matter. Do you understand? Now, we said that the relation between the actuated force, okay, and the two moments, the frictional moment and the moment due to the forces is mn minus mf c over c. The c is the distance, right? We talked about it. Now, it happens that when, remember, Shabab, the act, I mean, sometimes we have the drum like this, just like in our cars, and we might have a shoe here and another shoe here. And then you see there is a piston, there is a cylinder, which has basically an actuator that apply the force on both sides. So let me make it clearer a little bit. So imagine that you have here one and here. This is the forces. So they apply on both sides at the same time. Now this is the actuated force. Now, if you have a rotation in a clockwise fashion, the direction of this force is aligned with the rotation, and that's why this shoe end up being in a self-energizing condition. Self-energizing condition is the condition in which we have a subtraction, which means that by applying a load, the friction will help you reach to the maximum pressure. While for de-energizing, you're actually kind of adding these together. So if the right hand side get bigger, it means the left hand side get bigger, right? And what does that mean? It means that you are actually going to need more force. You will see it today in the example very clearly. With the same force, you can energize, with the energizing shoe, you can reach the maximum pressure allowable. But with the same force on the left shoe, you will end up with a pressure which is way less than the one on the right. Why? Because the rotation of the disc is the same. It's just if it is a clockwise, it's a clockwise. But the right shoe has the actuation going in the direction of the rotation, helping it out, and thus become what? Self-energizing. But a clockwise rotation with respect to the left shoe, where the force is applied on the left, will cause it to be in a self-de-energizing condition. And thus, one disc, two shoes, one of them is self-energizing, the other one is not. You see that? So basically, and then we said, okay, what are these moments? Well, luckily, this isn't very difficult. We have the moment equation given to you right away. This is PA, the allowable pressure. This is B. B is actually the width of the shoe, because the shoe has a depth, right? So this is the face width of it. So R is the radius, which we talked about. Is it indicated? Yes, over there. That's the radius. And then A is this distance from the pivot all the way to the center. And then we have sine theta A. You remember theta A? Theta A, we said it is the angle defining the location of maximum pressure. Maximum pressure. And we said for a short shoe, that angle is theta 2. For a long shoe, that angle is 90, period. Is 90. So you will see that you only need to integrate this, which is not very difficult. So it has been integrated for you. What you have here is a factor multiplied by all of this. This has to be evaluated. You need to substitute theta 2, then minus theta 1. You substitute theta 1, don't forget. And then the moment due to frictional forces is no more or less the same. This is the factor over here having F, it has a friction force. The friction coefficient. This doesn't have. This is related to the normal load. This is related to friction. So it has F, PA, B, R, and sine theta A. And we have the integral part where you had done the integration is a little bit different. That's it. Okay. You move further. This is the torque equation. The torque capacity of the brake is very important, you will see. And how do you calculate the torque? There, this is the equation. The torque, ya shabab, doesn't care about whether this is a self-energizing or de-energizing. What it cares about is, as we are going to see, is that the pressure in a self-energizing shoe is probably the maximum pressure, so you will use PA. But for the energizing shoe, you will end up with a pressure which is a little bit different. That's why you might end up with two torques, two different torques, but the equation is essentially the same. Okay. Then what did we say? We said, okay, we need now to know what are the reactions. This pivot, you don't want one day, God forbid, to have a problem while you are driving your car just because these two shear, forces cutting through the bolt, which is, holding the shoe, it's because of over design, under design. Like you did not calculate the reaction, and the reaction happened to be too much, and they cut the bolt, and then the shoe fell. You don't want that, right? So the reaction here are, as you see, they have a factor over there which consists of a pressure, BA, B, which is the width, R, the radius, divided by sine theta A. And then we have a factor A and B, coefficient of a friction, and we have Fx. And there we have Fy, we have F, which is the coefficient of friction, and again we have A and B. And also we have the same coefficient over there. What is A and B? A and B are two equations, which I'm going to show you later. But if X and Y are basically the resolved component of the actuated force, the resolved component of the actuated force. Now, you need to be very careful with these one. How do you resolve them? Here, the coordinate system is X and Y like this. So when you put the coordinate, a local coordinate system at the location of the actuating force, it has to be the same as the X and Y, horizontal and vertical, and then you measure the angles with respect to this one. Yeah. Now, later in the problem that we are going to solve, you will see that we are going basically to have an inclined coordinate system. So you need to incline the coordinate system at that location, and thus you need to be careful in determining the angle. Okay. Now let's move on. What is this? Is for actuating force on a clockwise rotation with self-energizing brake. Now, what if we have counterclockwise rotation for a self-de-energizing? Then we will end up with almost the same equation. There are only few minor differences. What is A and B? These are A and B, and you need to evaluate A and B for theta 1 and theta 2, and then you substitute them back. The good thing is that A and B applicable for the self-energizing reactions as well as the de-energizing reaction. You don't need to solve it twice. Once you solve them once, you can substitute them into these two equations and these two equations. You understand that? Okay. Now let's move on to the problem. The problem, ya shabab, which will take most of the time today, there we have a brake, okay, which is shown in the figure. The drum has a diameter of what? Let's say the diameter of the brake is equal to 300 millimeter, which means that the radius is 150 millimeter, okay? And it is being actuated by the same force. Look at the forces over there. We have a right shoe, we have a left shoe, and the shoes are identical and have a face width, which is B is equal to 32 millimeter. And what's next is that uh, the lining, which is the like a frictional material, is molded ab abysitose, abysitose, which is a material, okay, used for the shoe. No, it's not abysitose. Asbestos, I mean, having a coefficient of friction of 0.32 and a pressure limit of 1000 kilopascal. Okay, we want to estimate the actuating force. We want to know the braking capacity, the hinge point bin reactions. Okay, all right. Now, before we get started, let's analyze this first. First of all, we have a rotation which is clockwise, and we can see that this shoe will have the rotation going in the same sense as the actuating force. So this side is self-energizing, while this one is de-energizing. That's number one. Number two, if you look, I can make my life a bit easy by constructing a coordinate system as X and Y, like this. And as we know, we measure the angle from the positive x-axis in a counterclockwise fashion, and thus theta 1 will be equals to what? To 0. And then from here all the way to there, look at the shoe, we will have theta 2, which is equal to 126 degrees. Do you agree?
Yeah.
All right. Now, the next thing, what is C? What is C? C is the distance from the pivot all the way to the line of force, this actuation. So how much is it? How much, ya shabab? Anybody? 212. It is 100 plus 112. All of this. And now the little bit more trickier question is, what is A? We know, by the way, the radius is 150, but what is A? Do you remember what is A? A is the distance from the center all the way to the pivot. So what is A? How do we calculate it? This is A. Come on, it's not Ramadan yet. Are you sleepy?
It is a bit challenging, Doctor. Just a minute. Let me.
112.
Yeah. مفروض.
How?
Oh. Okay.
It's a 112 square plus 50 square under the square root. Yeah? It is the hypotenuse. Do you understand that? Now, what you should also know is that based on the fact that this force is here, okay? Now, the coordinate system, the new coordinate system with respect to that force is inclined by how much? By over here at 24 degrees. So when you take the force F, you should resolve it, okay, into a coordinate system which is inclined by 24 degrees. Do you see that? This is X and this is Y. And you will see that finding Fx and Fy will be, related to whatever I picked here as a coordinate system, which is, by the way, if you look at it over there from here to there, is inclined by 24 degrees. Do you see the amount of details? I think my iPad got disconnected. Yeah,
We
it is.
can see it.
You can see it. Yeah, there it
Oh,
is.
it's gone.
Gone. So this is a very long shoe, or a long shoe, and for that reason, theta A is going to be 90 degrees. So theta 1, based on the coordinate system, is 0. Theta 2 is 126. Theta A is 90. Therefore, sine theta A is going to be equals to 1. Okay? Now, what you should understand is the following. When we design and when we calculate, when we find capacities, we do it to the limit, right? That's why estimating F reasonably must be done. So even ya shabab, let's say in this problem we are going to solve the problem for both the left and the right. But let's say for whatever reason you are being challenged to make an answer very quickly, focus on the self-energizing. You will see now that the self-energizing will reach the maximum pressure. This will generate more forces and it will become way more critical than the de-energizing. Okay, so again, this is A, as I showed you earlier. It is the hypotenuse, the square root of 112 square plus 50 square. Then we now, so this is how much? 122.7. Just remember the number. Now, what do? We move on to the moment. So the moment due to friction is equal to, as you see, the friction, which was how much? 0.32. PA, how much? 1000. P, how much? It was 32 or 32 millimeter. And then R, 300 divided by 2, 150 millimeter. This one is 1. And then this is R again, 150. Theta 2, 26. A is 122.7. And that's it, you're done. The only thing you need to worry about is that you should be consistent with the unit. And here, it's been substituted as follows. This is F, no unit. This is PA in Pascal. It is 1000 kilopascal. That's why we multiplied by 1000. And then we have the shoe width, which is 32 millimeter. So it becomes 0.032 meter. And then the radius is 150 millimeter, which is 0.15 meter. Then you multiply it by R. This is R again. And then R cosine 120. And then A, the 122.7, we divide it by 1000 to make it in meter. And then we divide it by 2. And this is sine 26, 126 again. What did we get? We got 304 Newton meter. Okay. Now let's move to the next one. The next one, remember, once we find these, we can subtract them for it and divide them by C, and then we get F, the actuating force. So we move on to the next equation. The next equation is the Mn. Remember, this is now integrated. So we have PA, that's 1000 kilopascal, multiplied by B, which is 32 millimeter, multiplied by R, which is 150 millimeter, multiplied by A, which is 122.7 millimeter. But we need to convert these into proper unit, which is meter and Pascal, divided by 1. And then there is only one thing. So look, this is PA. This is what? B in meter. This one is R in meter. This one is A in meter. The only thing I want to warn you about is this. If you have an inside an equation, multiply pressure by radius, by diameter, whatever, and then you have theta over 2. If you substitute 126 over 2, this is wrong. Degrees, angle and degrees are not numbers. That's what we say. We say radians are numbers. So you need to multiply it by pi and then divide by 180. Yeah? This could be a common mistake. But the rest is simple. You have 1 over 4 over here, and then sine 2 multiplied by 126. How much did we get? We got 788 Newton meter. This is the moment. So now we go there and we say the actuating force is how much? 788 minus what? 304 divided by, remember, we said we add the 100 plus the 112. This distance plus this. This is the distance from the pivot all the way to the actuating force. How much is this? We got 2.28 kilo Newton. Okay, 2.28 kilonewton. Now, want to find the torque? The only thing we need to do, just to make it clear, is to put for the torque equation this little subscript r to indicate that, remember, this is not like 307, the raising torque, the lowering torque. This stands for the right shoe. Okay, the torque equation is F. So this is the friction, 0.32, multiplied by the pressure, which is 1,000 Pascal. And then we have B, which is 32 millimeter, and then R, 150 millimeter square, and then theta 1 is 0, theta 2 is 126, and sine theta A is 1. So how much is this? 366 Newton meter. Is that good? Any question?
None yet.
Okay. Now, let's go and look at the equation for the moment, right? So I'm just going to write them down quickly over here. So Mn is equal to PA multiplied by BRA divided by sine theta A. And then I have theta over 2 minus 1 over 4 sine 2 theta, and then theta 1, theta 2. Okay, what is MF? It is F multiplied by PA multiplied by BR divided by sine theta A. And then we have minus R cosine theta minus A over 2 sine 2 theta. And then we have theta 1 and theta 2. Now, why I'm writing this down for you? Very simple. Tell me, what do you think in here? What do you think in here is going to be different for the left shoe different than the right shoe.
Will it be in the opposite direction? The torque?
And understood. But now you can just simply flip the coordinate system in the sense that here you will have the coordinate system going like this. This is X and this is Y. And you will see that in reality, these two are not going to be different. The only thing which is going to be different is this. How? B is the same, coefficient of friction is the same, R is the same, A is the same, sine theta is the same, thetas are the same. So the only difference here is BA. So how? This is the allowable pressure. If the allowable pressure for the right shoe is 1000, why not the allowable pressure for the left shoe is 1000? Why not? Well, I kind of told you this in the introduction, but that's fine. Let me repeat it again. If you go back to the question, it says the actuating force is the same, but the right shoe, if you actuate it because it is self-energizing, okay, we decided to plug the maximum pressure. And what did we get? We got 2.28 kilonewton. So this is the story. 2.28 kilonewton on the right shoe will generate 1000 kilopascal on the right shoe, which is the limit, the maximum. How do we know this? Well, if you use 1000 in the equation to calculate F, then F is associated with that 1000. But if you apply 2.28 kilonewton in the left shoe, which by the way, you have no choice, it's a must. Remember, the actuator is sitting in the middle. It has two rods, one pushing in here, one pushing in there with the same force. So 2.28 will be applied on the left one. You have no choice. But because it is self-de-energizing, it is not necessary that 2.28 on the left shoe will generate 1000 Pascal, kilopascal. So in the book here, in the solution, what did he do? He said, okay. Then the only difference between the right shoe and the left shoe is the P. So instead of solving all of this again, okay, not this one, there, said instead of solving all of this again and all of this again, because if you solve it for the left shoe, do you know what are you gonna do? Do you know what are you gonna do? Let me first clean this. For the left shoe, if you solve this again, you will come here and substitute this one as PA. And what are you gonna get? You're gonna get a number, not this, you're gonna get some number multiplied by PA. And here, you are gonna substitute this as PA. So what are you gonna get? You're not gonna get this one. You're gonna get some numbers multiplied by PA. But the truth is, we substituted 1000 here, Pascal, kilopascal. So in the solution, what did he say? He said, okay, let me take the same value, which, by the way, was obtained from 1000 kilopascal, divided by 1000 kilopascal, and then multiply it by unknown pressure. Unknown. PA, which I don't know. And the same, take this one multiply it by PA, which is unknown, and divide it by 1,000, such that the pressure is in kilopascal. Okay, so what is happening here? If you look, the lift shoe is de-energizing, which means F is equal to Mn plus Mf divided by C. F is known, C is known. This one and this one are both function of PA. So what happened? What did happen? You will end up with one equation, one unknown. In another word, this equation will help you determine the pressure in kilopascal for the lift shoe. How much is it? 443. So, just to repeat, if you apply the same actual weighting force on the right and left shoes, okay, you will end up reaching for the self-energizing the maximum pressure, which is 1000. On the left one, you will only have a value of 443. And that's why we told you in the de-energizing shoe, that force, friction is against you. You need to push more in order to reach to the 1000. Here, we put what makes 1000 with the self-energizing, and it didn't even reach us to the half of the maximum pressure. Do you understand that? So now we determine the pressure of the lift shoe. If we determine the pressure of the lift shoe, we can find its torque. Exactly the same equation, but we substitute the pressure as 443. Yeah, we do that. And what do we get? We get the torque. You see, the only difference here is this. So how much did we get? We get 162 Newton meter. The capacity of the brake, the total torque capacity, is the sum of both, which is 528. Now, the other question that we were asked is to find the bin reactions. So if you recall, I told you you should find A and B by, knowing that theta A is 1, theta 1 is 0, and theta 2 is equal to 126. So now you go to A, you go to B, and you calculate them. Just don't forget, whenever you have an angle like this, you have to convert it into radian. Don't forget. So you get these two numbers, and then in the book, the solution here, it was assumed that you remember the coefficient, that we multiply the reaction by. We called it D. It's the same. Okay, so D here is equal to PA. This is for the right shoe, so we are gonna assume this. We are gonna substitute this one as 1,000. Yeah, and then we multiply the dimension in meters, and because this is 1,000 kilopascal, the result will become, this is actually like a force. So this is going to be 4.8, and it has a unit of kilonewton. Why? Because I put here a kilo pascal. If I put pascal only, then this is gonna come into Newton. Now, if I do this, now remember, all what I need to do is to go for Rx and multiply it by D, this factor, then A minus FB. And what? Minus Fx. And Fx is 2.28 sine 24. You remember when I told you the actuating force, you have to resolve it based on the coordinate system, which is inclined by an angle of 24 from the y-axis. Yeah. And then Ry is going to be equal to D multiplied by this factor. A, you know it. B, you know it. F, you know it. And Fy is actually 2.28 cosine 24. You do this, you will get the resultant load acting in the pins that are pivoting the shoe on the right. You do the same by changing the pressure right here into 443, you see? And then you will be able to estimate Rx and Ry, and then you get the reaction. Just look, the resultant load on the left shoe is 0.86 kilonewton, while the resultant load on the right shoe is 5.04 kilonewton. That's more than 5 times. Yeah. So it's a lot. So I mean, if you want to design this, definitely the right shoe is the more critical one. Now we have around 5 something minutes. So what I'm gonna do, I want to introduce you to a very interesting section, which will, by the way, will not take too long to finish, which is externally or external contracting rim. The title of the previous section was internal expanding rim. You expand it, and then the shoe become in contact with the drum, and that's how you dissipate the energy. Here, what happened? Whatever it is, a drum over there, okay, is external, and then on top of it, we have the shoe. So it is outside. Now, if you look, we are almost using the same terminologies. Here, we have a rotation, which is clockwise. We have a distance from the pivot all the way to the actuating force, which is C. We have a radius, which is a distance from the center to the outer layer of the rim. We have a distance from the pivot to the center, which is A. Everything is the same. We have an actuating force here. We have 2 reactions here. We have a shoe. By the way, let me clean it and then show it to you again. We have a shoe which starts from this is theta 1, and end in there, which is theta 2. And at an arbitrary angle, we can again resolve the forces into a normal forces and frictional forces. Now, what is the difference between external and internal? Well, first of all, with external, okay, with external configuration like this, you can see that a clockwise rotation is in the opposite sense of the actuating force. Therefore, a clockwise in the internal was self-energizing. A clockwise here is self-de-energizing. It's opposite. And the equation will accordingly be the actuating force for a clockwise will be Mn plus Mf divided by C. You see that? And there are a few little differences in the terms here between the external and internal, but everything look the same. We have Fx, Fy, A, B, F, BA, B, R, sine theta, everything is the same. Now, what about if we have counterclockwise? Counterclockwise will move in the same direction as the actuation, and thus it is self-energizing, and this is why we have a minus sign. They get subtracted, self-energizing, and there are again few differences. So what about the rest? The moment, the torque are exactly the same. So be careful. Whenever you have a brake, then you need to know, is it internal or external? And once you rule out the rotation and you know which one is energizing, which one is de-energizing, you just know how to use proper equations and you should be set to go. That's it. This is it. Okay. I think I reached my time.